We've had some pretty high-powered math. I thought 2 equals 1 plus 1 was maybe more the speed here. And just keep your eyes out as we're going for the places where the 11s and the Conways come in. First, I'm going to tell you a little bit about the Julia Robinson Mathematics Festival, which is something that Nancy and I have organized for kids around the US and started in the Bay Area at Google in 2007. And the basic structure of it came about because Nancy was interested in getting kids involved in deep problem solving. And there are already so many opportunities to do that kind of thing through math contests, which seem to be where all the interesting problems accumulate. But that leaves out a whole collection of kids who maybe aren't interested in speed or who aren't interested in competition. So we created this event to give an opportunity to work together on things such as building an octahedron out of ropes, and get kids involved in problems that are very accessible, that start with things like 1 plus 1 equals 2, and lead eventually to something deep enough that they really can't get to the end of it in the time that they're working on the problem. So the key element of it is that the kids get to interact with each other and with mathematicians who are not too helpful. Because our tendency is we have all this exciting math we want to tell everybody about, and we know all these things. But the really good ones know how to not be too helpful. So Donald Knuth was at one of our festivals, and he was sitting around a table much like the ones you're at with a bunch of kids working on some problems. And this little girl turns to him, obviously like boring old guy. I'd rather be talking to one of the grad students. They look cooler, you know. And she says to him, "Excuse me, can you help me with this problem?" And he looks at her and says, "Well, I don't know. Can you explain the question to me?" Okay, that's teaching, right? So that's the kind of thing we're aiming for with these festivals. And then, again, to avoid the competition aspect, we want to have kids going home with math toys and math books and puzzles and things. But since we're not going to have a winner, we raffle them off. So that's kind of the basic structure of the festival, is a room this size with math on all the tables, and just replace 80% of the mathematicians in the room with kids, and we're good to go. So I'm just going to talk about one of the problems, which is one of the ones you'll find in our gift. You can find a bunch more on our website. So we have 2 and 1 plus 1, 2 ways to make 2. We have 4 ways to make 3, which is probably necessary to illustrate that 2 plus 1 and 1 plus 2 are supposed to be counted as different. So we want to find out how many ways are there to write n. Not a particularly hard problem for people here, but we'll get to something at least a little harder. So of course we have to ask how many ways there are to make 11. And doing this with kids, we try to get them to do things like estimate, you know, where could we bound this thing? Teach them the skills they need of what to do when we need to cope with a hard problem, because kids mostly have experience doing exercises where first you tell them what to do and then they do it. And so make them find easier problems. If trying to find the number of ways to make 11 is hard, find the number of ways to make 4, you know, so on like that. And then find a way to organize. And it turns out that in doing this, organizing the collection of all the ways to make 11 in different ways, you pick up all kinds of interesting different bits of mathematics, and it turns out to be pretty cool. So some of the ways to organize, it seems like people naturally want to organize by how many parts, how many numbers there are in your sum. Another common way is to organize by the first part. That's probably the easiest. The size of the largest part turns out to be pretty interesting. I've been doing this problem with kids and school teachers for about 4 years now. And I just recently, a month or two ago, had somebody suggest, let's organize it by how many ones are in the sum. So you might have fun exploring that. I didn't know the answer to it before anyway. You know, so we pretty quickly see that if we organize it by first part, you have a pretty easy recursion, because if you're making 5 and you start with 3, well, then you have to finish with one of the ways to make 2. So there's those 2 ways to fit into the block. And so you get, if you organize how many ways there are to make going down the column, how many ways there are to make 7 starting with a 4, there's 4 ways, because that's the number of ways to make the remaining 3. So you get these powers of 2 with the ones repeated. So then the row sums are the powers of 2, and you have your answer to the original question about 11. Okay, or you organize by how many parts, and you see what's probably a pretty familiar pattern here. And then when you start trying to explain it, what you find is that, well, you can turn 5 with 2 parts into, you can turn 4 with 2 parts into 5 with 3 parts by adding 1. And you can turn 4 with 3 parts into 5 with 3 parts by adding 1. Wait. So in one case, you're adding 1, and in the other case, you're just sticking an extra 1 on the end, increasing by 1, maybe we should say. And so this kind of caveman style of writing things actually exposes a lot about how this problem works. You can organize it by largest part, and all of these diagonals in this diagram are constant after a certain point. And you might have fun figuring out 1, 2, 5, and 12 are the first 4 constant diagonals. So you might have fun figuring out if you organize it by what's the largest number in the sum, what comes up. There's some Fibonacci stuff that comes in, like how many ways there are to make 9 using only 1s and 2s. But who spotted the 11s in the Conway? I mean, 11's a divisor of 55, sure. But this is the second time Conway's been in the picture, at least according to one name for the puzzle that the kids are working on, is sometimes known as the Conway cube. And Stan Isaacs always brings us a big collection of those. So it turns out the number of ways to make 9 using only 1s and 2s is the same as the number of ways to make 11 using no 1s at all. And your caveman proof looks like this. And so maybe my original slide with the title of the talk should have had a sort of subliminal 11 disguised as a 2. Thank you.